this is just a few updates about what's been going on in the SPAC community, and a really brief overview of, I guess, the key differences with EasyBuild. So for folks who haven't used SPAC before, it's designed to look a lot like your mainstream package manager tools, but with the flexibility needed for HPC tuning. So you just clone it from the repo like this, and you source the script, and then you can run it, or you can just run it straight out of the directory. You don't have to source something. This will install HDF5 and all of its dependencies. I'm sure the EasyBuild folks are familiar with that sort of thing. But you can customize it. You can say, hey, I want this version of HDF5 actually, or I want it built with a different compiler, or I want it built with a different option, or you can inject flags in the build and so on. So you're able to sort of customize the build both on the command line and in config files. And, like EasyBuild, it's helped a lot of folks deploy HPC software faster. The SPAC community is growing. So, I mean, this started in 2013 with just me and a grad student. And then, we presented it at Supercomputing in 2015 and started getting contributions from lots of other places. This blue line here is if we had just accepted it, well, if it was just Livermore the whole time. And you can see that, without all the contributors, of which there's over 1,000 now to the repo, or some way or another, we wouldn't have gotten very far. So SPAC really depends on this community of people to keep running. As far as I can tell, we have several thousand users on the doc site. We hit around 7,000 monthly active users, I guess, this past month. I don't know how well that correlates to actual people. It's probably slightly less, but it's used around the world, and it's gotten to be a pretty big ecosystem, sort of like EasyBuild so far. And Kenneth mentioned in his talk that if you looked at the user types and the countries for SPAC and EasyBuild, that they would be pretty different. So I thought I'd show those. We've been doing the SPAC survey for 3 years now, so we have some of the same data. You can see that the SPAC community is a lot more evenly distributed. I'd say the makeup of the community has stayed about the same since we started asking this question in 2020. What are you? I'd say 40% software developers, 34% scientists and researchers, and probably a steady like 20-ish% sysadmins and user support staff. That's not so different over here. We just gave people more categories. So RSE is a category here. So is software developer. It turned out a lot of the software developers, actually an increasing percent of them, wanted to identify as RSEs. In 2022, we still have a pretty steady percent of system admins and user support staff. It's still about 20%. And there haven't been that many major changes there. There's a larger chunk of people who want to give us their own job category, even though we have tons of ones in the survey. So that's this little section over here. So I think if you merge this with some of the others, they get slightly larger. For the percent of folks using SPAC in the USA, I thought it was interesting over the years. We asked both, where are you from, and and are you in the US exascale computing project for the SPAC survey? And so the ECP percent has gone down this year by quite a bit, by about 10%. And so has the percent of people in the USA using SPAC, while the user base has gone up. So this year, I think most of these responses are actually from Europe. We didn't get that many from other places. So, I mean, you could probably say that SPAC is around 40% European at this point, and it's only 60% USA, if that, this year. So there's the breakdown. So if you think about SPAC at a high level, there's really 3 parts to it. There's this syntax that I showed where you can customize installations on the command line. Each of these is sort of constraining the installation and saying, hey, install this version. You can leave it and not specify all that and just get sort of the default some version of the thing that SPAC will give you, usually the latest. Or you can constrain things. This tells you, what the requirements are for the user. And that syntax is used both, on the command line and in config and in packages to express dependencies and things like that. The second piece of SPAC, in addition to that spec syntax, is the packages. And so I don't know how easy this is to see in the room, but SPAC packages are basically Python classes. They give you, a home page and a URL, which is metadata. This says there are 3 versions available of this package, each with a checksum. So that says you could build it 3 different ways. These are the variants down here. You could build it with and without MPI, with and without OpenMP. And then these are the dependencies down here. It depends on MPI when MPI is enabled, and it depends on CMake as a build dependency, and it needs version 3.0 or higher, and so on. So this metadata part is really just constraints. I think it's less repetitive than easy configs, where you have to write the same version constraints over and over again and copy paste them. And you can't do things like ranges. So we have ranges in here. This tells you all the possible ways to build a package. You can think of it as specifying a space instead of specifying a bunch of point configurations. And then down here, the methods in the package are really just telling you what the build recipe is. So this says, hey, enable OpenMP equals something depending on whether OpenMP is enabled. That's the variant from the spec. You're translating the configuration you're handed by spec to build instructions. And then down here, this package is not a great package. It doesn't have an install target, so we just built one to copy the executable in. There's more. There's things like conflicts. There are patches and stuff like that you can put in a package file. A lot of that should probably be familiar to folks who are familiar with EasyBuild. But the key difference is really just that we're specifying the space of possible builds. And then on top of packages, we have something called environments, where you can make a YAML file with a bunch of config to manage sort of a unified software stack together. So you could have HDF5, libbelf, OpenMPI. You could keep listing those. You could put constraints on each of those lines. You could pull in some configuration that says, which compilers to use and so on. And we will, take this whole thing and install it and spit out a log file of what got installed. And so this sort of tells you the concrete version. So you can think of a log file kind of like an easy config. It's got all the sort of concrete specifications in it for the one configuration of all of this stuff that spack chose for you. And the kind of cool thing about this is you can version the YAML files and maybe the log file if you want to in a repo and hand it off to your team to reproduce some build that they've done. And you can think of the YAML one as sort of the functional reproduction of the build. Like, so we need these 3 packages. Maybe they have specific versions. And the log file is like, no, build exactly this. Build exactly what I told you to. And then finally, the last thing that you sort of need to think about for a mental model of spack is concretization, where essentially we get all these contributors. We get command lines like this. The contributors put constraints in the package files. There are lots of different configuration files in spack and environments like the one I showed. All of those really are providing constraints to this concretizer, which does a big solve and comes out with the sort of fully resolved DAG of what you need installed. This isn't uncommon for dependency managers. I mean, most of them have a solver in one way or another, except for things like Nix and actually EasyBuild. But in spack, we're solving for a lot more things. So like all the dependencies a large fraction of the dependencies are conditional. We have lots of options on packages that other package managers probably wouldn't give you. You have a lot more freedom with what your choices are in terms of what gets installed. So that's sort of the high level overview. So I thought I'd talk about the latest release. The last year I talked about the new concretizer that we integrated into spack. That's been in there for a while now. So 0.19 was released at SC22 in November. It is the last spack version that'll support Python 2. So we've already removed support in the mainline, and the next release won't support it at all. We don't support Python 3.5 anymore. We basically picked 3.6 because it's the default on RHEL, and it seems to be the lowest version that anyone wants to support right now, or that you would need to support out of the box to run on a system. So we're only doing 3.6 and up now. And then we've added progressively more features to spack as the releases have gone on. The latest one is you can actually put requirements, like hard requirements, in your configuration. So in an environment or in a packages.yaml file, you can say, yeah, we want 1.13.2. Our site really needs that version, and we need it required as a hard requirement across the board. We can do things like require one of 2 options as well. So you have to build mpitch with either CUDA or ROCm support, depending on what's supported on the machine. So essentially, this gives you a lot of the power that has traditionally been in package.py files, but in YAML. So you can do it in configuration. You can supplement your package.py files with hard constraints now in the config. We added some improvements to environments. So it used to be that we would concretize everything in an environment separately, which meant that you could get sort of varying versions of dependencies. We made unification true the default now. So an environment really is like one consistent environment, at least by default. If you are a facility, you would probably set this to false, or to when possible, where we essentially say, okay, you gave us 4 different MPIs to build, and so we'll let those vary, and we can have different versions of them. But we'll try to make them share dependencies as much as possible. So you have, controls like this on what the concretizer is going to do, what the solver is going to do behind the scenes that, tell you how you want your dependency tree laid out. We've tried to make spack a little better for developers. So previously, things like spack install and uninstall in an environment would work a lot like a virtual env in Python. And that was sort of the intent of environments originally, was to provide something kind of like that, where you could install, your own Python stack or something like that. But increasingly, the spack environments have been used for configuration as code. And so, what people tend to do is they'll take a spack YAML, they'll stick it in a repo, and hand it off to the rest of their team. And when install and uninstall, if you said like spack install HDF5, it might have previously gone off and built you a new HDF5 that wasn't really specified in the YAML, or that wasn't the version that was in the YAML. It would concretize it again and say, okay, I'll make that one for you. And it would modify, either your YAML or your log file. We've made it so essentially you have to add and remove things from the environment, so manually. So you either edit the file and edit the list, or remove it from the list. And then you can think of the file as like Rails. This is your stack. You have this set of things that you can install or uninstall, and install and uninstall really just install things that come from the stack when you're in an environment now. And we found that dev teams like this a lot better, in the sense that now they only have 2 places to think about, kind of like with Git, when you add and remove things from your Git index, where you're really modifying what's going to get added to your environment. So I think it works better as a workflow. You can still do those things in one go. We have --add and --remove options on install and uninstall. But it's much more like a skeleton now, that you can hand around to people to sort of manage a single installation that evolves over time, or a single stack, or like some combinatorial stack. So I think this works better. We've been thinking about workflows a lot. One of the big things that we added recently, which sort of came after we added Windows support last year, was package recipes can now support multiple build systems. So instead of just the simple recipe I showed before, you can now have something that has all the constraints in one sort of top level package, but then you can have 2 builders for it. And so this has been useful because we've seen, the main motivation for it was that once we switched to Windows, a lot of packages would sort of regress. They wouldn't use our built-in AutoTools package or CMake package. They would sort of regress to one that supported both, where they would build, one was the project's default build on Linux, and one was the project's default build on Windows. So we would see like CMake and NMake, or AutoTools and NMake, things like that. And that wasn't great, because it meant that people were sort of going outside of our built-in support for a lot of handy things that are in these like superclasses for CMake and AutoTools. So we spent a lot of time building infrastructure to make these adapters, so that essentially now you can either write your package the old way if you support a single build system, or you can factor out the builders and have 2. And that's nice, because all the constraints on the package go up in the main place, in a single place, so all the different versions that can be built. And there's this extra variant now that tells you what build system it was built with. And then you can consolidate all the code for the different build systems elsewhere, or maybe you don't have to do much down here other than specify the arguments for CMake and configure. And this has also been helpful because a lot of packages are switching to CMake, or switching build systems. We've seen things switch to like Meson and so on. And often we need to support versions of that package that have 2 different build systems at 2 different versions, or 2 different build systems at the same time, and so on. So now that's sort of smoothly integrated. We introduced some cool concretizer features to allow a little more control over propagation of flags. So it used to be that variants and compiler flags behaved a little differently. The compiler flags were automatically propagated to all the dependencies to keep them consistent, or at least by default they were. And then the variants only would apply to a single node in the graph. So if you asked for A plus V, you'd get a graph like this, where none of the other things had V applied. And people really wanted to be able to say, no, I really want all of my CUDA dependencies to have CUDA enabled, and so on. And so now we have a syntax for that. You can say plus plus or tilde tilde to propagate, an enablement, a disablement, or you can say double equal to propagate like a string value through the graph. And if that variant applies to something down there, then we'll enable it. And likewise, you can use a single plus or minus or tilde like you always have been able to set values for a single node. So you get a little more control over your graph. We have added more Git versioning. And so as Spack has become used for more developer workflows, we've added the ability. So we had the ability to specify commits. So you could say Spack install foo at some Git commit. Now you can actually say, git.develop, git.0.19 for different branches. You can also force Spack to interpret that as a particular version. So you can say, I want to build master as though it were version 3.2. And the kind of nice thing about this is it really forces you, it allows you to lock down exactly how Spack is going to build something. The reason that you need to map a Git version to a regular version is because the packages are written generally. And so Spack has to decide what version is this branch. And we can do a little bit of that with tag introspection. So we'll look at your repo and say like, okay, there's a tag here that says v 3.2. So we'll treat it as 3.2. But if that's not there, you need a way to lock that down. So we have we now have these concrete Git versions where you have git.commit equals some some actual version to interpret that as. So people have seemed to like this. It lets them it lets them specify their dev environments a lot better. This is probably the most relevant one here for folks running on Cray systems. We have been working with Cray for, HPE now, for a long time via El Capitan and Frontier, which are both under the Coral 2 collaboration. And we got them to add a lot of things that make the Cray programming environment a lot less modular and stateful. And the two big ones were that we got them to add standalone Cray compiler drivers, so you can run the Cray compiler without having to go through CC, which is sensitive to modules. So you can invoke Cray CC directly now. And we got them to add back the MPI wrappers that they had butchered out of Cray MPitch and were not including in the distribution. And what that means essentially is that now you don't have to think about modules in the Cray environment at all, and we're not going to do that going forward. You can build straight from a prefix, and you can configure your compilers in a way that's not sensitive to the user or the site environment by just saying, here's an external package. Cray MPitch is installed in this prefix, that's it. Don't try to load a module that changes on every PE update to deal with that. So we found so far that, this has enabled us to build our normal Linux environment alongside the Cray environment at Livermore Computing. And so we just rolled that out for our machines. And it's also, it has made the builds way more reliable from PE release to PE release. We don't have to worry about what new environment variables have been added or removed from Cray's modules. And it makes things way more reproducible. So this is how we're going to use the Cray environment going forward. You can still say you have an external module in Spack, but you might not do that. We encourage you not to do that. We're not taking the ability away. And then there's also there's a JSON file that gets generated by Cray that actually tells us all the externals that are in that environment that we can read. And it's in opt-cray PE. I think it's called manifest under that directory. If you want to go and try to parse it, it looks like a Spack database, but it's pretty simple JSON. You could probably learn what's in the Cray environment just like we do in Spack if you wanted to parse that thing. And then finally, something we introduced in the latest version to try to deal with the sort of DDoS your file system problem that emerges when you use a lot of shared linking. We have this new linking mode in Spack. We've always done RPath in Spack, where basically all the libraries know how to find their dependencies. RPaths are still paths. And so if you end up adding a lot of RPaths to a library or an executable, when that library gets loaded, the OS still goes through all those RPaths and tries to find all of your needed libraries in them. And so it's still a search. And that means there's a lot of stats and or opens and other file system operations that are going to get done. And those end up, causing problems for your file system at scale. We've introduced this sort of pre-bind mode for linking where instead of searching any paths, we just replace the needed libraries with absolute paths in the binary. to their location. And so in the DT needed, that used to be like, foo for libfoo. Now it's it's the full path to libfoo.so. And so when you load your executable, at least for all of the libraries that are in its needed section, we'll just open them and we won't have to do a search. And that reduces the metadata accesses considerably when you start up your program. All right. We're working on a lot of things for 0.20. This is sort of in the ISC timeframe. We're going to have a drop directive for if you inherit from the built-in packages, you can say, hey, drop all the regular versions. I only want these versions. We're adding concretizer options that sort of control where you can reuse packages. We're tightening up version syntax so that we can be a little more exact about versions. So previously, Spack really only had something like a version range where you could say, like, I want version 4.5, which would match like 4.5.1, 2, and so on as well. We're adding @equals so that you can say, no, I really want 4.5, just 4.5. And that's allowed us to specify that, certain patches only apply to certain very specific versions, especially for projects that don't really adhere to SemVer in their versioning. There's testing improvements, a few other things. I think probably the interesting things for these folks, or the most interesting thing here in the context of maybe EC is, we're looking to add a libc compatibility model. We currently label the things that we build in Spack with the OS they were built on, but that's really not necessary because the only thing that we're using that as a proxy for is the libc on the OS. And so we've added some detection logic. We may end up just ripping out the OS tag and replacing it with this libc tag that would just let us run the binaries in places where they make sense, based on whether it's muscle or libc or a compatible version of libc that the libraries were built with. We don't 100% know what to do with externals there yet because externals to some extent rely on way more than libc. And historically, you've kind of been on your own with that. How that factors into what we put for the OS, we may just keep the OS tag or keep it and libc for the external. So we're thinking about that. And then for the SC timeframe, we have a bunch of sort of longer term things that we've been working on. We were trying to improve the error messages so that we can sort of explain why Spack made the decisions that it did. And say, this package required CUDA. This one has a dependency that says that it can't work with CUDA when it's at that version. So, you can't put these three things together. We'd like to be able to say that to the user in a more intuitive way, so they don't have to figure as much of that out themselves. We're working on getting compiler dependencies so that you could depend on, C and then have a particular compiler implementation picked that supports the version of C that you wanted, so that they work like our other virtuals. And then we're working on spliced installation of binaries. So essentially you could say, hey, I have a system MPI. I want to install those packages from a binary cache that were built with mpitch. And I know that mpitch is compatible with my local MPI. So I want you to just rpath the system MPI when you relocate the binaries, as opposed to installing the binary from the build cache. So I think this will be really nice once it's working, because it'll enable us to actually ship binary compatible libraries for HPC systems that you could just install without building. So we're doing a lot of work on binaries for Spack these days. All right, so that's about it for the updates. One last thing I wanted to talk about was CI. I think, folks, if you look at the way that Spack works, I think this is pretty similar to EasyBuild. Essentially, we have all these external contributors on GitHub who are contributing to the develop branch. We release branches off of that every once in a while that stay stable, and we backport bug fixes to those, and then things like E4S, ECP's software distribution that has like about 600 packages in it, sort of branch off of that, or sometimes off of develop. And these are the things that and they go and integrate with the software at the facilities. Application teams that use Spack can consume packages from all these different places. They can say, hey, I want to use something from E4S. I want to use those binaries. I want to use the facility installation as well for something else. They can mix and match the different components. But currently, the thing that we're missing is that this stuff down here, where we actually end up integrating with facilities that are not very open and cannot really run their own CI for us on upstream. This last mile effort gets to be a lot, because it sometimes ends up being just a port of what's been happening on develop. While develop has CI that moves along and gets tested on every pull request, the facilities can kind of get left behind because we can't run as much automated stuff there. And so we set out like last year to make a binary distribution for spack that was sustainable, that we could basically keep building as part of our normal contribution process, where people just submit pull requests. We wanted the builds to happen as part of that and for them to get tested before they ever got integrated into develop. We wanted it to be sort of rolling, where we have releases for develop, and those basically get populated every day, every hour. And we have releases for the actual releases of spack, where we basically snapshot the binaries that we want at release time, and you can install them later. We wanted to be able to support eventually all 6,900 packages. We're building something like 4,600 things repeatedly in the cloud now, so that I think we're getting close. And we wanted to ensure that you could still build sources on top of this stuff, and that it was secure. So we set up a CI system where we're using GitLab with GitHub. We can take a spack.yaml and we can generate a bunch of CI pipelines from it. And so this is an example of something that we can do with spack environments that's nice. Like, you specify the stack here, you can generate a graph that gets built on lots of different platforms and that gets tested in all these environments. We have pipelines in AWS. We have a bunch of more interesting machines at University of Oregon. And finally, we've gotten permission to use, at least at Livermore, the CrayPE container, or a containerized version of the CrayPE that we make ourselves, in the cloud for this type of CI. We can't distribute binaries for Cray yet because that was a bridge too far for the Cray lawyers, but we do have permission to do CI for it. So I think we'll be doing these builds soon. And then all that happens, and you get your pipeline passed on GitHub, and so it says the pipeline passed on GitLab on GitHub. You see that, and then we only allow things to merge once all these tests have passed. This has been cool, but we wanted to be able to take this CI work and make a binary cache from it, and so we built. Let me fast forward ahead here. We built a fairly large cloud-based system to do the CI for this. And so, we have resources running in AWS. We've got the binaries distributed around the world with CloudFront and S3. We're running sort of a Kubernetes-based build farm in here that has a high availability GitLab instance, a bunch of runners with a tool called Karpente to farm out containers to those things. And then we have runners at the University of Oregon and a bunch of monitoring. And we have this little bot that you can talk to on GitHub to sort of interact with the CI system. We'd like to have more real HPC test environments, but working out the security for that, where you're basically letting pull requests run at HPC sites, is hard. And so we haven't really done that yet. The University of Oregon is more open than most of the DOE sites. We've separated the build environments for PRs and develop. We really want to be able to test on PRs because that ensures that nothing that's broken goes into the main line of spack. And so when contributors submit package changes, what we figure is that if you trust spack, you trust the maintainers. And so when things first come in for a PR, they haven't been reviewed by maintainers. So we build them in these sort of untrusted environments where we're saving binaries that we don't really intend to keep around. We're just using these to see if things build and to cache the builds there. Maintainers review the PRs, and then once that happens, once they've had a look at their recipes, we end up rebuilding everything in a more secure, sort of protected environment over for the develop branch or for the releases. And so the develop and the release branches get built independently of any of these PR binaries. So essentially, you can't sneak something into a binary in a PR and then push some code that sort of makes it look like it's not there, even though it's still cached, and then have that make its way over into develop. The develop stuff and the release builds are built entirely from things that the maintainers have looked at least the recipes. And we're not scanning like sources of packages or any of that at the moment, but this at least, I believe, makes the binaries at least as trustworthy as the sources that you were building from before. You're trusting the maintainer's recipes, essentially, and the checksums that you have for the source tarballs. So we announced this last year at ISC, where we made this easy workflow for contributors. It's fairly easy to add the binary caches to your spack installation and install from binaries, at least partially. And so that's been out there for a little while. And what we've done lately is we've learned what could go wrong with building a large scale CI system for tons of builds. We learned that there's a lot of balance between doing this dual build environment and picking essentially there's a balance between what you build on PRs and how often you build the main develop build cache. And so, if you happen to have a build of develop that you've done, and you get a PR that's merged off of here, what GitHub would normally do is merge this with the head of your repo. And you don't get a lot of binary reuse out of that because there are changes in between that you're testing sort of inadvertently. And so we've learned that, what you have to do is merge this with the last full binary build that you did on develop, so that the build tests are only happening on the changes for the PR. And if you get PRs that are up here that are beyond the last build that happened, because the branch tends to run ahead of the last build, then you have to hold these guys up. And you need to wait for this build to finish before you can start testing these PRs. And so there's a balance there in that, if these things fail, or if things tend to go wrong on develop, then it can take a very long time to get PRs in because you're waiting for these develop builds to catch up. And so, there's also a question of how much stuff should we be testing on PRs. At the moment, we only test direct dependency or direct dependence on PRs. So if you change like zlib at the bottom of the stack, we'll only test the things that directly depend on it. That seems to have worked pretty well, but it's still a lot of builds. And so we may sort of adjust what we're doing in CI to see how predictive it is of things actually working when they get into the main develop branch. We're still working on the balance. And there's also things that you have to watch out for, like if you're doing lots of builds, there's a lot of potential for system failures. And so if there are subtle errors happening in Kubernetes or on your builder nodes, and they are failing these pipelines, it doesn't take very many system errors across the board to fail enough pipelines to make it painful for users. And so we don't want people to have to babysit their pipelines. And so we've been looking at that. So one thing we did recently was that there were a lot of failures on our pipelines back in February, and we didn't really know why. And so we sort of doubled down on the monitoring. And so we've built a bunch of dashboards that can show us what's going on in CI. So we can see, the total build time that we consume in CI for these packages now, which is pretty cool. For some reason, ParaView consumes an awful lot of build time. And so we're trying to figure out why it is that it's so much bigger than like even LLVM, TensorFlow, or Trilinos. We figure these ones seem like usual suspects for us, but we figure ParaView ought to be kind of like Visit. And you can actually see the number of pods, which are containers, that get allocated to different PRs over time. And so we have this dashboard that shows you all the PRs that are currently building, and or that have built in the past time period that you asked for, and how much work we were doing on them, how many jobs were they really consuming in CI. So this has been useful for understanding the load. We've configured CI to support lots of different instance types. And so we're doing this so that we can take advantage of spot capacity. The more different instance types you can ask for, the more likely you are to get a cheap instance with the spot pricing instead of the on-demand pricing from, say, Amazon or in other clouds. And so you can see here that we have tons of different instance types that we're building on, and we may cram lots of different jobs on those instance types. One kind of cool thing about the CI system at the moment is that you basically give it archspec tags, and you say that I need this build to happen on x86 64 v3 or v4. And we build for that target. And so, even though we're using all these different instances, we are not getting effectively different builds across all these different types of nodes. We're compiling on an instance that's compatible with the target that we're asking for. But we're able to, if we have like a big cascade like node spun up, and we have some small jobs that could, or some builds for like not AVX 512 that could run there, we can still run them and pack them onto nodes. So we've been working on that. And so, like I said, in February we had a lot of problems with pod scheduling, and we didn't, or with well, at least with reliability. We would see a lot of pipelines fail, and so users were complaining. People get irate when this happens. And we looked at the monitoring, and we were getting like 12% failures across our jobs, which actually translates to something worse across pipelines, because the pipelines have lots of jobs in them. And so if you have a 12% failure rate across the board, you're going to get some angry users who have system failures on their pipelines. And you can see that like in this period in February, we did have sort of a preponderance of errors happening. So we built this dashboard that tells us the types of errors that are happening. We're trying to make different categorizations of them so that we can sort of monitor what's going on in CI and see what are the big errors that are happening right now. And that's been good because now, this 12% that we had here, we have reduced to like a 2% failure rate. And the 2% is really mostly like spack errors and build errors. So like the things that you would expect to happen in CI. And we have a way lower percentage of failures now. And kind of cool about that has been that that also reduces the cloud costs because we don't have as many users saying, "Hey, rebuild my pipeline, rebuild my pipeline." And I think we're able to do a better job of monitoring this now. The problem that we discovered here was that this Karpente tool that manages all those different instance types, it's really designed for persistent services. And so one of the things that it does is that it will go and kill containers so that it can consolidate VMs. So essentially it'll say, okay, you've got one container running on this node right now. And instead of draining it like an HPC queuing system would do, where you let the batch jobs finish, it would just kill it because it would figure it was some stateless thing that it could start up somewhere else. And that wasn't good. So we learned a little bit more about Karpente configuration. That has helped a lot. There are a few other sort of nagging errors that we stomped out with this monitoring, and now we're in a way better state than we were back in February. And we have a number of dashboards now that we can look at, like this is job failure rates. We have another dashboard that'll show us like pipeline failure rates over time, which is really more of a measure of user impact, because those are it tells you, what are developers experiencing right now, as opposed to just your raw job failure rate, which can kind of understate the degree to which errors affect users. All right, so takeaways: the SPAC community continues to grow. We seem to at least this year have had an increased number of European users. I don't know if that's going to continue or not, or if that's just a one-off based on how we did the survey, but that's always good. SPAC has a lot of users in Europe already, so I think that's good. We're moving fast on feature and package development, so there's tons of features going into each new SPAC release. Lots of work on core to sort of model the software as it is, and to make sure that we can handle all the increasing complexities of the HPC software ecosystem. And then CI is helping us keep the stack stable, so that's good. We've had people way happier with the reliability of the recipes since we started doing them in CI, and then better monitoring is helping us keep the CI stable. And so who keeps the monitoring stable? I don't know. I guess we'll learn that as we go forward, but it seems like the monitoring at least has stayed up so far. And I think having this kind of system for your build farm is pretty helpful. So that's it. I'll take some questions.
Okay. Can you hear me, Tom?
Yep.
Right. Do we have any questions in the room? Well, people think about this. There's one or two online. So in the Zoom, Andrew is asking, are there documentation or tutorials on using the new Cray XC setup? The spec documentation seems to cover only the old approach.
Yeah, we need to update those docs. We don't have documentation specifically on that right now, but I mean, essentially you can just say, here, you can add an external the way that you normally would and put a prefix there instead of a module. That's basically the difference. If you run spack compiler find, it'll detect the compilers that way. We're going to update the docs pretty soon.
Yep. Okay. Another question, and I have a related one. Does the binary cache do the binary caches need to be versioned against spec version? So one of your slides, 25, seems to suggest that. And how many versions are kept around? And my related question is for which operating systems and which versions are is the binary cache supported currently?
So no, they don't need to be versioned with spec versions. They're at least backward compatible with spec versions, as long as we still know about the package right now. There's a PR in to remove a couple places where we need to know we need to have a package.py file around for a binary that has a given name. That's going to go away, and so you won't need. You should be able to use a binary regardless of whether you have any package files sitting around for it. So what was the other question? What OSs and things are we building right now? Yeah. So we are building at the moment, depending on the stack, for different OSs. So like for the Amazon stack, we're building for Amazon Linux, which is Red Hat compatible. We don't have all the compatibilities rules in place, and that's kind of part of this libc feature that I'm talking about for the next version of spack. We really want the things that we build on essentially Rocky 7, which is what Amazon Linux, or RHEL 7, which is what Amazon Linux is, to be usable everywhere, because they should be. They're not really built against anything that would prevent them from being used that way. And then the bulk of the stack is built for Ubuntu. And so we've got Ubuntu 18 in there still. We're going to upgrade that to 22 for the next release. And so we'll be building for latest Ubuntu across like the E4S stack and the One API stack. The other thing that we're going to have for ISC this year, or at least that we're working on, is cache.spack.io doesn't do a really good job of telling you exactly that, which is what people want to know about binary caches. And so we should have a way better overview of the stacks that are available, what to do to use them, and so on for ISC. So you can actually look at the caches and say, okay, here's what I add to get these packages, and so on. So does that answer your question?
Yeah, I think it does. Maybe the final one, Adam had a question: when is spack 1.0 going to be available?
Why do you guys care about numbers so much? I guess. It's like, yeah, like, you know, we show you the big CI system that we use to test the releases, and everyone's like, but it doesn't say 1.0 on it. What's the matter with you guys? So yeah, I within the next year or two, I would say there's a couple things we want to do before we go 1.0. The main one, or I guess, so the main one is compilers as dependencies, which I put on the 0.21 release list. We really want to get that refactor done because it affects all the packages, or it could potentially affect all the packages. And so once we do that, we could have a stable package API, and we want to split the package repo out from the main spack repo at that point. It's not like we don't make the packages backward compatible right now. It's just that we're a little worried that with compilers as deps, we could make some breaking changes, and you know, we don't yet want to factor out all the packages when that could happen. So I think with those two changes, we would go 1.0, and you know, maybe we should have gone 1.0 a long time ago and just called it that, and you know, continue releasing major versions when we break things. But I don't know, at this point, I think we'll make 1.0 a big deal when we do it, and so you know, we don't want to blow it on the wrong release. So that's why it's taking so long.
Does that mean there will be a party, and will we be invited?
You guys are always invited to the spack party. It's going on all year round.
Okay, good. Thanks a lot, Todd, and enjoy the rest of your day.